Good evening and welcome to the APAC edition of the Professional VMware vBrownbag podcast. I'm Alistair Cook. It is the 22nd of May. It's nearly June already. And I'm joined again by Irfan Ahmad. Irfan, how are you this evening?
Doing very well. Thanks for having me, Alistair.
Hey, it's a great pleasure and an honor to have you join us. Carrying on from where we were 2 weeks ago, with looking at performance shapes and particularly thinking about how we can use the vSCSIStats tool to look at what's going on inside our machines and hopefully then tune our storage to suit them. So I'll hand over you. You're leading this one. So where are we going today?
So last time we talked about workload shapes and introduced the concept, and actually spent quite a bit of time, more than 45 minutes, really just getting into the depths of what they mean, how to analyze them, what type, and different examples. We went through a lot of motivation, and I'd encourage folks who encounter tricky storage performance problems to go back in the archives and take a quick look at that podcast. Today I'm going to continue from where we left off and just add a little bit of context and intro, but continue forward from where we left off and then get into some more advanced use cases and a demo of how to go about and actually collect this data and how to make sense of it.
And for those who have watching the iTunes feed for the vBrownbag, you will have noticed that we're quite a little behind on processing for the APAC edition. These will turn up over time, of course. If you're listening on iTunes, then they've already turned up.
One of the things that we talked about last time was, how do you go down and track and how to really determine storage performance problems or planning for storage, upgrades and so forth, how to tune your subsystem, your storage subsystem, when you're running virtualized workloads in particular, to be able to handle new workloads that are coming, or to just be able to consolidate more and add more workloads. So a lot of times the typical question around this is, I have a bottleneck and I need help in overcoming that performance bottleneck. And the first question is really, is the disk even a bottleneck? And that's very, very important to try to understand, because as we were talking about last time, that while I was at VMware, where I was lucky to be around for 9 years, and worked on all kinds of tools, one of which we'll talk about today. I worked for a while in the performance team, and anecdotally, about 90% of the issues we would see would be somehow end up being resolved by some modifications to the storage subsystem. But despite that, it's very important at the start to take a look, because a lot of times the storage performance issues are the most complicated ones and the ones for which the tools are least capable. And you almost want to eliminate CPU memory and networking issues earlier in your debugging process, just in case you get lucky, because they're a lot of times easier to solve. But yeah, the first step is a disk even a bottleneck? And then, how do you determine if that virtual machine, the workload that's having the performance problem, will benefit from any type of tuning? I'm just listing caching as an example here. All these things require detailed workload characterization, and here's some examples on the slide of those characterizations. Outstanding IOs analysis, read-write ratios, latency, cache hit ratios if you're dealing with a cache, and many, many more. And there's really no simple rule of thumb to apply and say, well, such and such workload in customer A's environment, or according to the white paper of a vendor, behaves in such and such way. Classic example for this is if you imagine Microsoft Exchange running the email system for a couple of different companies. And you think, well, it's Exchange. Maybe the workload should be the same. But imagine for a minute, one of the enterprises is a print shop. And all the emails coming into that print shop are megabytes big, maybe even 100 megabytes big. Now imagine that workload versus the workload of a system administrator like us. And what we're getting are very tiny, small emails all the time with alerts and alarms and thresholds being crossed and so forth. And so the workload is going to actually be very different than that. And you know, just applying communal knowledge on these things, it doesn't always work. So no one size fits all. So that's pretty grim, right? But not so grim if you have access to the tools that can help you with this. So for us, we're going to be focused on workload shapes, of course. That's the topic of the session today. And the technique for workload shapes for us is going to be histograms. As you know, histograms are representations of a distribution, not just a single point like an average or a median. So an example of that is here. So let's say that we plot the latency, and this is a made-up example, but it's illustrated. It's very simple. You'll see here the latency of some operation. In here we're plotting it microseconds, let's say. And you'll see right away there's like two clusters. There's some effect here that is being not just uniform or not just around some cluster, some Gaussian distribution. This is a bimodal distribution of the latency. Not sure why, and a lot of times it's not easy to figure out why these things happen, but it's very common to get this sort of behavior. And what you see here on the y-axis is the frequency. So for more than 1,000 IOs, and let's assume these are IOs, were completed in less than 3 microseconds, between 2 and 3 microseconds. And about 500 plus IOs were completed between 1 and 2 microseconds. And that's the way kind of you want to read a histogram. A histogram is all about the y-axis always being the number of events is on the y-axis, and then the x-axis is the actual range of values. Now notice in this case, if this was actually a real example in any one of the tools that we're used to using, and the tool will be reporting a single number, and that is typically the mean. Now, imagine the mean being 5.3, and there's never even a single IO that is ever completed with that value, and yet all of our tools are telling us that this workload has a response time of 5.3 microseconds. And so those single numbers can be very misleading. And just more generally, why would you take one number if you could actually have the distribution and actually see what's going on in more detail, which often is the set of clues you need to go and actually optimize or solve or troubleshoot your problem. And as I'm going, please feel free to ask questions. Alistair's watching the feed and would love to kind of solve and illustrate things as we go. So the workload shape technique, being histograms in this case, is implemented in ESX. I implemented this in the core ESX product starting in ESX 3.0, 2006. And so it's been in the product since. And the way it works is on a per virtual disk basis. So it's very granular. If you had 2 different disks for your workload, you could individually separate out the workload shapes for each one of those. So for each of the virtual disks, the system is tracking the characteristics of all the I/O going through there in multiple different ways. And the way histograms work very efficiently in ESX or any other system, by the way, this particular technique is only available today in VMware's products because none of the other hypervisors actually has a workload shape gathering system for IOs. So let's say that this is the current shape of the histogram for the size of IO requests, which is actually really important if you're going to try to understand, how to tune your system, how to tune your RAID striping, for instance, and other things for the purposes of tuning a particular workload. So let's say this is the current histogram, which means there is only one IO that has so far been seen in the IO size range between 2K and 4K, right here. And then between 4K and 8K, we've now seen 5 IOs. So let's say a new IO comes in and it's 4 kilobytes big. And the system is extremely simple. It runs in the kernel, very efficient. All it does is says, well, there's a new IO of size 4 kilobytes, so I'm going to go and add one number to the bucket here, which is the 4K bucket. So there it is. That's all the system does. Extremely simple. And the result of it, though, is that over time, as these things fill out, you get the distribution. So let's look at the type of data that's collected in this way. So we have the read-write distributions for all of our histograms that we're going to talk about. And so let's look at some of these histograms. So you have the I/O size. That is the example that we just looked at. And that represents the total, the size of the I/O coming from the virtual disk. So from the virtual machine on that virtual disk. So it could be 1K, 2K, 4K. It could be a really odd number, somewhere in the middle between 2K and 4K. We see that sometimes. It's really difficult to optimize for those types of workloads that have irregular sizes. Or more typically for a Windows type workload, you'll see 64K IOs. Some workloads that we'll look at today, you can go to 1 megabyte IOs, input backup, file copy, and those sorts of things. Then we have this really interesting histogram called seek distance. And that gives you the distribution of how far apart on the disk are the IOs that are coming from the virtual machine. And so the further apart those IOs are, the more the disk has to seek, and that's why it's called the seek distance. And as we know, seeking on a disk is very expensive because the disk head has to rise up and then float across and then resettle on the new cylinders. So it's very expensive. And that's why random workloads do poorly, because they force the disk to constantly be seeking. So in this histogram, what we'll be looking for is a way to understand, look, how far apart are the subsequent IOs coming from a virtual machine? And if you see a seek distance histogram with large distances recorded in it, that tells you it's a random workload. If you see a seek distance histogram with a very tight band of IOs, in other words, the seek distance is very small, say 0 or a few sectors, maybe even half a megabyte or a megabyte, and you know that the workload is fairly sequential. And that has a huge impact on performance. And knowing that is very powerful. And there's really no tool today, even on the disk array side, that can tell you the sequentiality of a workload. And in this case, the vSCSIStats is able to capture that very trivially and make that available. Extremely powerful. You know, I really wish more VMware administrators and IT architects dealing with storage would learn about this tool, because for those who have used it, and you can find all kinds of blogs if you search for vSCSIStats online, it really changes how you view your system. Then we have outstanding IOs. This is a notion of how many IOs are queued from the virtual machine at a time. Gives you a notion of the parallelism of the workload. Then we have the IO inter-arrival times, and that gives you how far apart is there some distribution of the time between multiple IOs coming from the virtual machine. And finally, the result of all of those characteristics from the workload and the actual behavior of the physical device results in latency. And we saw kind of an example of that earlier. A couple of situations where you can have bimodal latency, and that's a great clue. So if you have access to the overall read-write ratio, right, you can answer dozens of questions. For example, are writes smaller or larger than reads in this workload? Very, very interesting. It allows you to tune reads versus writes for your critical workloads very easily. Are reads more sequential than writes? Again, very interesting. Write sequentiality is very easy to optimize for in some cases. In other cases, it doesn't matter. Say for NetApp, it hardly matters. But for reads, it's a significant difference in performance versus random and sequential, and that you might need to be doing all kinds of tuning of your disk array to deal with this. And then sometimes you have different latency being incurred by different types of IOs, and how is that going to get explained? So this is the refresher of how the technique works and what types of questions you can answer using it. So now let's go look at an example. We went through a very large number of practical, real examples in the previous podcast, so I encourage folks to go take a look and use those examples to learn how to troubleshoot coolant workloads. But I wanted to take a look at a new one this time. So this is Windows file copy. And this was run a little while back, and so I had access to a couple of virtual machines. One was a Vista, and one was an XP Pro, just for illustrative purposes. And I decided to run file copy. And something very interesting comes up when you take a look at these plots, and I'll explain them in a second. So the top plot here is seek distance histogram. As I mentioned earlier, if you see a lot of activity in the in the middle of this graph, so around 0, then that means it's a sequential workload, because that really illustrates that there's only a small distance between IOs. And if you look at the, if you see any kind of activity towards the negative or positive infinity of that top graph, the seek distance histogram, that means it's a random workload. And what we see here is that Windows XP is behaving very differently compared to Windows Vista. And the odd thing is that XP is issuing a lot of IOs, and that's why you see a very high peak in the middle there. But not all the IOs that it's issuing are sequential. You see some at the edges. This is very odd. Why is that Vista is issuing so few IOs for this file copy? And otherwise, the workloads are the exact same size files being copied in both cases. Why is it issuing so few IOs? To really understand that, we now look at the IO length histogram. And what we'll see here is that Windows XP Pro is issuing IOs around 64 kilobytes in size, and a very large number of them. Whereas Vista is issuing 1 megabyte IOs, so larger than 512K in this case, and I happen to know this, 1 meg IOs. And so the result of that is that it's obviously going to incur much fewer number of commands to issue, but also that the IOs being very sequential, large reads and then subsequent large writes, allows very little seeking between the original location of the file and the new location of the file. So a quick example, right? We were able to see both the sequentiality pattern of this very simple workload as well as IO length, and be able to explain why it is that Windows Vista is so much better at file copying, so much faster, and while issuing so few IOs. And very typically, of course, you don't really know as an infrastructure administrator, as a VMware administrator, what workloads is running inside the disk. It might be some custom application, might be a classic application running in non-trivial workload that you're not really aware of the exact patterns. So whereas in this case I happen to know what it is, but if you just look at the graphs on the right, not knowing what the workload is, right, all these clues help you understand the performance and tweak it. So now let's take a little bit closer look at a little bit more detail. So one of the things that I realized early on talking to customers and looking at the patterns that I was seeing in my experiments back in 2006, 2007 timeframe when I wrote this utility, was that it's interesting, weird things were happening in the way that operating systems and applications were issuing I/O. And remember, the histograms are very, very efficient at representing distributions, and the VM kernel and ESX is extremely efficient. But what happens to allow them to be efficient is that they only record ranges. So that posed a problem, because what I would see would be all kinds of IOs that were not exactly 4K, a little bit less, or maybe 1.5K IOs. And those are really difficult to tune, and are oftentimes the bane of the existence of storage administrators trying to optimize storage arrays. So I decided to do something a little bit unusual, and I've actually not seen anybody else do this, and it balances efficiency as well as being able to keep a little bit more data for this sort of thing. And I'm just mentioning this here because if you ever do run vSCSIStats at home, you'll find that you might run into this and not really know what Irfan was thinking when he implemented this. So I just wanted to explain that up front. To make the histograms practical, I made the bin sizes on a very irregular scale. So an example of that is, let's say, the IO length histogram. In this case, you'll see a bucket that is 2K, and then you'll see a bucket which is a little bit less than 4K. So 4095, one block less than 4K. And the reason why we do that is so that we can distinguish between IOs that are exactly 4K, which are special block sizes because storage arrays oftentimes optimize for those sizes. And so we can single them out if we have a bucket specifically for 4K, and then the bucket to the left is the 4095 bucket, and that basically captures all the IO between 2K and a little bit less than 4K. So the moment that you see a peak in the 4K case, as you'll see in the little plot on the bottom right here, you know that it's actually purely 4K IOs, and that's really good because you can deal with those easily. But if you see like a 2.5K or 3K, 3.5K kind of an IO, that'll end up in the bucket to the left there. So it's very important to know if the IO was, say, this power of 2, 16 kilobyte size, or some other IO size between the range of 8K and 16K, and that can be captured here. So it's a little jarring when you look at it the first time, but the moment you realize why it was done, it ends up being quite powerful. Okay, so now let's look at.
It's nice to have that explanation. I've seen those columns before and thought, what the heck is going on? And I understand a log scale, but why is this just weird division? And yeah, now it kind of makes a lot more sense. And it's one of those funny things where you make a small change to how you record things, and you get vastly more information out the end of it.
Yeah, and I've actually solved serious problems as a result of having had access to this just a little bit more information, like you said, just like there's just like no other way for somebody to figure out what those odd block sizes are doing. I mean, really, there is zero tools in the world that will help you figure that out. Mm. So I originally did not have it, but I kept running into, when I was testing it in those early days, before ESX 3.0 shipped, I was testing it in a lot of different workloads, and I just couldn't figure out what was going on. The buckets didn't make any sense, and then finally it clicked that look, these odd IO sizes. So if we look at how this is run, it's actually extremely simple, and I'm going to provide a demo in a couple of minutes here to illustrate how trivially easy it is to run. And as we go through, we'll talk about some future roadmap things that I'm working on to make it even more easy for everybody out there. One of the things that in all the versions of ESX since I believe 3.5, not only has this capability existed, but also there's a user level tool that ships with ESX that actually has that utility that allows you to go and control these and visualize them and so forth, or export them for further analysis. So what I've got here is two different histograms. The one on the left is the IO length histogram, and the one on the right is the latency histogram. So let's talk about them. When you see the histogram output, you'll see at the top a description of the histogram. That way, if you're saving it away somewhere, and when you return, that you'll have access to what that histogram actually was. And when I actually give you the demo, you'll see that I've actually, for the purposes of fitting things into the slide, I've actually elided some more information in here, which is which actually even has more tidbits in it for saving away in case you need to come back and take a look. You'll see something very interesting here. So the first thing that you see in this histogram output is the min. And what that means is that in the time period that you were measuring, what was the smallest IO length? Because that's the histogram we're looking at here. What was the smallest IO length that was observed? Then you'll see what was the maximum IO size that was observed. The mean, which is a constantly updating mean, and then the total number of IOs that were seen in this period that are represented in the histogram itself. So very interesting information right off the bat, even before looking at the buckets here for the distribution. Then we come down here. So this will take a second to explain, but it's really important to get this. And once you get it, you can, it's like the matrix, right? Once you Once you get it, you can actually just look at it and visualize. It looks like a lot of numbers at first, but once you realize what's going on here, you can visualize this without needing any graphs. Of course, you can always take it to Excel to report up, or to show a storage admin or somebody who doesn't understand kind of the textual output here. But for your own purpose, once you realize what's going on here, you won't need Excel. I never actually plot in Excel these things unless I have to present them somewhere. And so here's how it works. So what you'll see is less than or equal to right here, and a number. So that means that the I/O length, what are all the I/Os that had length less than or equal to 512 bytes? And that's, when you go to the next bucket, that means what are the number of I/Os that were seen, okay, that had a I/O length of 1024 or 1 kilobyte or less. Now, of course, in this case, it's a range, so it's 513 to 1024. So what is the count that had that? Then we'll see, starting at 1025 till 2048, how many I/Os were seen that had that block size? And then starting right above 2K to almost 4K, that you see the 4095 again that we talked about in the previous slide. And how many I/Os? And right away you start to see, oh my goodness, whatever this workload is doing something really funky, because it's issuing I/Os that are like 3.5K or something, and not exactly 4K. And yeah, this is really odd, but it does happen. Similarly, you have 4K here, so that will be exactly 4K because there's no distance between 4095 or 4096 and 4096. So this is exactly 4K I/Os. You ideally want to see the majority of your I/Os be aligned to 1K, 2K, 4K, 8K, 16, 64, 128, 256, or 512K I/Os. Those are the ones that the storage arrays really know how to optimize. Everything else causes them problems. Alistair, do you think it's interesting for me to describe why those I/Os cause problems?
I think it would be a useful context, yeah.
So the reason why this is so important to track is that the storage arrays typically have some sort of a cache size, so like a block size in memory. So suppose you do an I/O and all that the I/O is, let's say, 1 byte, the small, or say 512 bytes, which is the smallest possible SCSI I/O. In SCSI, you can't do less than 512 bytes. The sector size, which is typically 512 bytes, or sometimes in modern arrays can be 4K. But whatever that is, that's the minimum size you can do I/O for. So let's say that you do 512 byte I/O, but the storage array's block cache is aligned to 4K, or actually usually it's 8K these days. Now all of a sudden what you've done is that you have forced the storage array to do an 8K I/O, bring that entire 8K I/O into memory, assuming it's a read, and then from that 8K return the 512 byte that the VM actually requested. And so basically what you've done is you have done two things. One, you force the storage array to read more data than the I/O required. So that could be problematic because you're forcing it to do more work than the application needed. Second of all, because you have to store all of that in the memory of the storage array to then be able to serve it out the wire into a VM, that you have taken up more area in the cache, which means that other important blocks that you should have been caching to accelerate the workload may need to now be kicked out of the cache because now you had to store this really large block even though you didn't need it. So this sort of internal fragmentation, as well as the extra work and energy that the storage array has to put in to go and get the I/O, causes performance problems that can actually be very, very severe in real environments. And so if it is the case that you know what the block size of your applications are, and especially with tier 0, tier 1 workload where every ounce of performance actually matters, that you can actually then go and tweak things. You can go and put them on a controller where the size of block size of the storage array cache matches more closely what the size of the IOs that is coming from the guest. So that's why this is actually something as simple as the IO length histogram is that actually ends up being very critical for performance optimization. So as you go down in this particular workload, the maximum we're seeing is 32K, as we already saw from the max parameter recorded up here. But this is a very quick overview of the IO length histogram, and you'll see that as you get used to it, very quickly your eyes will follow along and say, well, right away, okay, well, the majority of the IO is 16 and 32K, and most of the other sizes are not that big. There are some odd sizes, but yeah, this is okay because most of the sizes will be kind of in the range where the storage arrays can do it well. Now, if you were to plot this in Excel, what will happen is that you'll be doing a bar chart, and all these ranges here will end up looking like what we showed here, right? So they'll be on the x-axis, and the frequency will be on the y-axis, but that doesn't really work for textual output, so they're rotated here. The second one here is latency. So this is really interesting because the latency, the way the vSCSIStats measures it in these buckets here, is in a resolution of microseconds, and there's very few tools in the VMware ecosystem that can actually go into microsecond range. So it's again, it's very, very valuable. So right away you'll see that the smallest latency we've seen in this time period is 191 microseconds. This is a really nice cache hit somewhere in the storage array. And the maximum we've seen is 13 milliseconds. So okay, that's not bad. 13 milliseconds is reasonable. And the mean is about half a millisecond in this case. In total, we've seen 288 IOs. And so you see the distribution right away. And the same way that you get used to reading the IO length histogram, it's the same sort of thing here. You'll see where the weight is, where are the big numbers, and you read across and you say, well, the big numbers are between 100 and 500 microseconds. That's really good. Let's move on. We don't see a problem here. Of course, in other realistic scenarios, this is going to be more complicated. But really what you're looking for is where are the big numbers and then reading across. Okay, so that's a quick overview of how to take a couple of outputs for a couple of different histograms and quickly read it for quick understanding and quick workload shape analysis. I'm going to give a demo, but before that I just wanted to say, a lot of times when you talk about any kind of performance data gathering, rightly so, folks are concerned about the performance overhead. Now this data was collected many years ago, and modern processors are so much faster. There's been 2 or 3 generations of major microprocessor x86 processor improvements since then. And so, we're at the point now where if you try to measure this, even many years ago when I did this, it was within the noise. But today, if you were to actually try to measure this, you wouldn't be able to. There's really, to collect the histograms, you cannot measure the impact because, as I mentioned, it's extremely efficient in the way that it's handled. So we've studied it from an IOPS perspective to see, is there a difference in IOPS? Is there a difference in the throughput? Is there a difference in the CPU utilization? And also the overall latency that the IOs are taking. And then also we've looked at the standard deviation of these numbers to try to understand, look, is there increased range of those numbers even if they are more or less the same. And so in much older microprocessors, there is a slight impact, but it is so small that it's extremely difficult to measure, and you have to be running for a really long time to really be able to measure it. But again, in modern processors that you could buy from Intel, or that you have been able to buy from Intel for many years, you cannot measure the impact of this. That's how efficient the system is.
So you must get a little bit cross when people talk about, say, about not running vSCSIStats and monitoring workloads because of the impact on the workloads, when you've got this sort of figures that says, well, you really can barely measure the impact of monitoring.
Oh yeah, I mean it's I have run it in 100,000 IOPS sort of environments and still not been able to measure. So that's how efficient this thing is. Once you get into multi-million IOPS sort of systems and have vSCSIStats on all the time, then you might be able to actually kind of get a measurement that's reliable and do it. But how many of us are running multi-million IOPS sort of environments? So yeah, I mean, I
Most of us
recommend,
can't afford to run multi-million IOPS.
That's right. I certainly can't.
I got a question from my friend Andrew over in Melbourne, one of the vMug leads in Melbourne. He's just asking, how much has vSCSIStats changed over the years? You were building this originally back in ESX 3.0 days, which was the beginnings of when I was an instructor 8 years ago. In the intervening time, how much change has occurred on vSCSIStats itself?
You know, there are over time a couple of histograms were added, and over time an extra set of features went into vSCSIStats to not just collect histograms but also collect traces of I/O, and those traces are basically just a block pattern of all the I/O coming out. They don't actually contain any customer data, any visible data, or anything like that. Just a pattern of I/Os for later processing, post-processing for much deeper analysis that even the histograms cannot do. But fundamentally, it is pretty much the same, and you know, there is, you know, the system is so simple that you know, it's got self-automated tests built into it, and really, you know, hasn't gone through any significant change since I would say about 2009 timeframe.
Cool. So a nice stable product that you got right the first time.
Yeah, yeah, and I've never had a single problem reported from the field. You know, I left VMware at the end of 2011, and so it was in the field, used by customers for at least 4 years, 5 years at that time, and I had never had a single issue with the customer running into a problem using it, and so that was nice. So yeah, I run it in customer environments all the time, and I never have a concern about stability of this thing. So yeah, so please, if you ever see anybody inadvertently, unknowingly spreading a myth around the performance overhead of vSCSIStats, if you're logged into ESX and you're running it from the command line, there is no overhead at all. So if people trying to do this remotely will obviously have overheads because you're moving data through a pipeline. But if you're running it locally in ESX, there is no issue at all. This is kind of like ESX top versus remote ESX top. If you try to do remote vSCSIStats or anything like that, then you just have a lot of text processing overhead. But it's got nothing to do with vSCSIStats. It's all about the transport in that case. So I think maybe you take a minute or two and start to look at some stats. So what I've got here is the CloudPhysics testbed, internal production testbed. Actually, it's not even a testbed. It's actually a production server where all of our code repositories run, our vCenter runs on top of this, and so forth. So so why don't we go in and take a look. So there's no other command in ESX that starts with the VSC. So it's right, nice and easy. You don't have to type the whole thing and remember the capitalization. You go VSC, tab, you get vSCSIStats. And let's just press enter. So you'll see there's very nice detailed help. You don't need to go read any blogs to be able to use this thing. It's extremely well documented, even from the command line itself. And so the first thing we're going to do is we're going to look at this flag called -L or --list. And that's really neat because it gives you the list of available virtual machines as well as their virtual disks in this environment, which is really nice because you don't have to go to vCenter while you're debugging to go and figure anything out. You don't have to be mucking around with vSCSIStats to even just get a listing. In fact, I know several admins who, whenever they're on the command line in ESX and need the list of their virtual machines that are currently running, they don't use any other tool for that. They just use vSCSIStats, even though they're not using vSCSIStats for actual histogram gathering. They're just using the -l command because it's easy for them.
Yeah, it's easier than trying to remember the rather arcane command line that you'd use otherwise.
Yeah. So here what I did, just to show you guys again, I just did vSCSIStats -l, and the output is right here. So you see virtual machine, you'll see the display name of the virtual machine. Okay. You'll see there's two virtual disks that are connected to SCSI0, SCSI1. For instance, here you'll see SCSI0, 0 and SCSI10. So that's just a different configuration. This example here was a single controller, 2 SCSI disks, and this one is here is 2 controllers, 1 SCSI disk each. So very quickly, I mean, this is our, like I said, this is our internal production environment, and you'll see all kinds of different virtual machines here. And the one that I'm looking for is this one right here. So this is our internal vCenter server, and all of our test beds and everything runs against it. And so here you'll see 2 numbers: the world group ID and the handle ID, the vSCSI handle ID. So we're going to quit out of this. We're going to then go in. Actually, we'll just remember this for now, and we'll say, well, I don't know. Let's say you don't know what the next step is. You know what the virtual machine is, but you just don't know what the next step is. So we're going to go back into vSCSIStats and say, okay, well, I've done the list now. Now I want to actually start. So -s will start. Okay. If you want to stop, -x will stop. Okay. Very simple. So we want to start, and there's a couple of different ways to start. So one way to start, remember, I'm doing this on my production machine, so I'm so confident that I'm running this on our entire internal production team, and I think you guys should be as well. It's that safe. So I've got vSCSIStats here. I can do 2 different ways of starting the stats. So one thing I can do is I can say -s, and that's it. Now what I just did was I enabled vSCSIStats for every single virtual machine and every single virtual disk in the entire system. Now, this is a 64-core box. It's huge. It's running a lot of VMs. And every single one of them is currently collecting vSCSIStats. So this is kind of the big bazooka. And I don't really need to collect stats on all of them because I happen to be setting just one VM and one virtual disk. So I'm going to just turn it off. So you'll see right away vSCSIStats-x will stop. So you see it goes through the entire list and stops all the vSCSIStats collection. So, all right, so that's the basic way, which is kind of the big bazooka, turn it on for everything. I kind of don't want to do that. I just want to look at one. So let's go here and say, well, how do I specify exactly, specifically which virtual machine and which virtual disk I want to go run? So the flags for that are -w for the world group ID of a VM and -i for the handle ID. So remember, we have already done the work of figuring out which VM we're going to use, but I forget. So let's just go and look that up again. So here it is. Here is the virtual machine, and so we're not going to go into vSCSIStats-start. Remember, that's -s, and then -w, and that's the 10577, and then -i for here. So now, of course, if you don't specify -i, it's still okay because it'll just iterate over all the virtual disks of that VM and enable it. In this case, there's only one virtual disk, so it doesn't matter, so I'm not going to specify it. And so vSCSIStats start collecting histograms and collect them only for this virtual machine. So I do that, and immediately I'll get a message saying, hey, everything's fine. I'm starting to collect the stats. Everything's good. Okay, so now the question is, now what? Now what do I do? I've already started the collection, but how do I get the data out? Well, conveniently, right next to all this enablement set of flags in the documentation here, there's a -p flag, which is to print. So this is a print histos command. And again, there's 2 ways to do it. One is to just do -p and just type all, or actually specify the type of histogram that you're looking for. So what we're going to do is we're going to go ahead and try the I/O length histogram. Okay, here again you can specify -W for the case for the particular virtual machine that you're trying to print the stats for. But since I already only have one running, I'm going to ignore it. But let's say you had it running for all workloads, but you only wanted the output for one of them, you could specify the work group ID and the handle ID, and it would only print for those. Okay. So keep it simple. I won't do that here.
And that'd be useful for getting stats about one of the disks on a virtual machine. So getting maybe if you got a database server and you just wanted to look at the stats on the log volume, you could use the handle ID on that one.
Exactly. So so we're going to go here and say I/O length. I want to look at only the I/O length histogram for that VM. And here we go. So this is now we have the I/O length histogram for that virtual disk, for that virtual machine, all recorded here. Okay. And it's really nice that the output actually has the full details in case you ever wanted to go look that up again, including the SCSI handle. So you see that there are some I/Os in this workload. This is running vCenter, remember, the VCVA. And there's some 512 byte I/Os that are being issued, some 64K I/Os, and the mean is 8K. Again, the mean, there's probably was not a single I/O issued of that size. And so if you just went by every other tool that you could find, you'd see 8.8K as the size of I/Os coming from this workload, which does not make any sense. And so we look at this and say, okay, well, the biggest number here is at 946. So let's look at that. Well, that's 4K I/Os. Okay, that's good. And then what's the next biggest number? Well, that's 8K exactly. Okay, that's actually pretty good. And then the next biggest is around here. So that's less than 16K, but greater than 8K. That's a little odd, and so on and so forth. So you go down this analysis, and you can get a very quick notion of the I/O lengths here. So now let's go and do a little trick that I like to do a lot. Is I will run a command, very simple, watch. If you don't know what watch is, it's a little program that will run the command that you give it every so often. In this case, I'm saying run it every 1 second. And it'll just refresh the screen with it. And that way you can just monitor. It's really, really nice. So I use this all the time. It's a great tool. It's available on all flavors of Linux. And kind of a simplified version of it is available in ESX. I literally use it every day. And so here I'm going to run it. And what you see is watch actually prints out the high-level stats and says the way that you're running watch right now is every 1 second it's running this command and just refreshing the screen with it. And so let's watch this, right? So right now what's going on is live, we're going to see every 1 second activity. So we just saw these two rows update. So right now there was I/Os that are happening continuously, and we get to see how this virtual machine's activity and behavior is. Now, there's no tool in the world that can give you statistics on an I/O by I/O basis on a real-time basis. And it's at your fingertip, right? You can log into ESX anytime and go and take a look at this. And this is kind of downtime right now during the day. This is constantly changing, and you can track it. Of course, you can also go and just reset it. Okay, that's -R, and come back in, and everything is 0. And then from there, we get to actually watch very quickly how those numbers are adding up. And bursts of activity and when it slows down and all that sort of stuff. So it's actually quite nice. So now I wanted to actually go in and say, instead of I/O length, let's go and take a look at latency. And here is when things start to get really, really interesting. So this is our production vCenter virtual machine that I'm using here. And you'll see that the vast majority of I/Os are actually completing in less than half a millisecond. Okay, But there are some IOs that are completing around 30, between 15 and 30 milliseconds, which is an eternity for a disk, right? In fact, we just had an IO go past 30 milliseconds while we were watching between 30 and 50, and 11 IOs were recorded there. So yeah, maybe for vCenter this is not a problem, but imagine running an OLTP workload, and some of your IOs, and in this case it looks like about 10% of your IOs are more than 15 milliseconds. Again, no tool out there is going to give you this level of granularity on an IO by IO basis. But what that allows you to do is to say, okay, look, I've got a long tail problem. My transaction processing workload is actually getting these really, really long tail. Like we just had a 100 millisecond IO go through right here. Remarkable amount of latency. And so in some workloads, that level, is a 10% of IOs being above 15 milliseconds, can actually really hurt the application and cause all kinds of problems. Hadoop workloads have suffered from problems if this happens, transaction processing workloads and so forth. And to be able to have that level of granularity, not just averages, remember folks, that's the key here. You look at averages, you're not going to be able to solve the problem. Look here. The average in this case is 2.8 milliseconds. And yet, you know, we're seeing 10% of the IOs of this workload be more than 15 milliseconds. And so there's a great set of clues here. And sometimes what you see is you'll see a peak here and then another peak here. So you see 50% of IOs being cache hits, let's say, and this is really a cache hit situation here. So then let's go take a look at seek distance. And what you'll see here is that if you look at the seek distance for this vCenter workload, that actually let me go and make this bigger. Okay, so the seek distance for this workload is largely kind of in this range here. So it's largely in the range of a few megabytes away from sequentiality. So blocks are close by, so vCenter is doing some kind of I/O pattern which is not exactly sequential, but not exactly random. Now, random would be if the majority of the IOs were in this range or in this range. Okay, but the fact that they are a little bit closer to zero right here in this log scale, pseudo log scale histogram here, that shows that there is like a, you know, 16, block 16 here is about 8K away from, IOs are 8K away from each other in these cases, 16K away, and so on and so forth. So by the time you get to here, you know, you're looking at a quarter of a megabyte, half of a megabyte away. So for modern disks, that's actually mostly sequential, but not exactly. So what you're looking for here is, you know, where's the density? Is it in the middle here, like in this case it is, or is it on the outer edges, like a lot of OLTP workloads? And right away you can use this information to go and help out as well. So now we look at this and it actually makes sense that a lot of the I/O is actually half a millisecond range because there's actually a lot of sequentiality or close by axes so the disk does not have to move. So now we can actually start to explain the data that we see in one histogram by the data that's in the other histogram and build clues and solve really thorny problems.
And then we can also infer from that there's, what is it, around 600 out of the 2,500 IOs that we've seen are sitting at that plus 500,000 and minus 500,000, which probably coincides with those long latency IOs as well. We have got some significant seek.
Precisely. Yeah, absolutely right. That's exactly the right way to look at this. So, so you know, so far what we've done here is we've looked at a bunch of different histograms. We've gotten a tutorial of how to run this tool. And in terms of histograms, we looked at the I/O length histogram to try to see, hey, how does that affect storage array caches? We looked at the I/O latency histogram to say, well, this is the I/O by I/O analysis, real time, of what the workload is seeing. And the fact that you can see the long tail there is remarkable. And you can have a much better conversation with an application administrator who is seeing some transactions that are taking long in his application monitoring tool. And this is actually, I would say, a call out. I would love to hear back on Twitter or and just pick up your email client and email me at irfan@cloudphysics.com. I'm collecting scenarios, anecdotes from people to write a blog about this or even an article about the difference between what an APM tool, which is usually real time and actually recording transaction latency on a transaction by transaction basis, and the mismatch between those monitoring tools at the application layer and the tools at the infrastructure layer that are looking at average 5-minute average or 1-minute average, even 20-second average tools. And what that's going to do is going to wash out all of these long tails, and we saw that here. The mean is in 5 milliseconds right now, and yet you have 20% of the IOs now that are more than 15 milliseconds, and there's too much data that's lost by those tools. So just email me. I'm collecting anecdotes and using that to come up with a way to actually improve these sort of tools for the benefit of sysadmins everywhere. And then we also looked at the seek distance histogram to wrap up, and just again, and started to look across this data to infer all kinds of patterns. And you're not going to do this for every single virtual machine and every single performance problem, but having this set of tools in your arsenal and in your tool belt will help you solve key performance problems for your critical workloads, and do it efficiently and quickly, and do it in real time, and not have to go out and make purchases of new hardware or do drastic measures like isolation when you don't need to. So there's a bunch of different use cases for this sort of thing. Analyzing a new disk performance-sensitive workload that incoming into your environment that you don't know much about, you want to go and learn it. Or maybe you want to tune the underlying disk subsystem. Maybe you want to do real-time performance monitoring, and this is a great way to do that. In fact, it's the most real-time tool in all the software tools that are available. The way you want to look at this data is that you want to pay attention to the changes in the distribution as well as the magnitude. You want to look at different metrics. Probably start with IO size. I typically start with IO size. You go to outstanding IOs and the read-write ratio. Here's a practical example. This is Microsoft Exchange, and in this case, I actually plotted them in Excel. It's very easy to do that. There's a bunch of tools out there from great bloggers who have actually written little scripts or Power CLI scripts to go and take the vSCSIStats data and convert it into these histograms. And what you see is that Microsoft Exchange seek distance is very random. So you see, you'll see a lot of randomness, which is big spike here, as you were saying, Alistair, right here. But not all of it. Just like the VCVA that we looked at, there is some locality. It's not quite 100% sequential, but it's close by. It's like a stride pattern. IOs are 8K away from each other, or 16, 32, up to like a megabyte or two away from each other, which disks can do really well with. And this was for reads. The writes, same pattern. There's randomness, and yet there's also some sequentiality. So that's good to know. This sort of bimodal spatial locality pattern. But you look at IO length for Microsoft Exchange, this particular version, you'll see that, yes, 8K is the most common, but there are larger block sizes as well, going all the way up to 128K. And then you look at the read traffic. In this case, I plotted this over time, and before we started the podcast here, Alistair and I were kind of looking at this, and looking at the outstanding IO histogram across time, and the time dimension is kind of going into the paper here, and seeing that the read traffic here is pretty steady. So the number of IOs that are outstanding at any point in time across time is pretty steady. There's a little spike here, but it doesn't repeat itself very often. But the writes are very bursty. Okay, so again, if you want to tweak your subsystem, you have to know whether you're dealing with bursty or steady traffic. And then something really interesting happens here. You see IO latency histogram over time. In this case, time is going into the paper on the left here. You see two spikes here. Okay, you see some percentage, small percentage of IOs that are seeing 500 microseconds range latency, half a millisecond, but you see the majority of them taking 15 milliseconds. And this right here is actually really interesting because you know that you could hitting some sort of a performance pattern here, and this is where looking across comes in. And if you look at this carefully, you realize, okay, that's a kind of a cache hit or a very fast IO. I wonder where the fast IOs are coming from, and you kind of come back here, and as Alistair was noticing in the earlier live example, that those cache hits are not really cache hits, or those fast IOs are not cache hits really, but rather they're this semi-sequential workloads. That's why you're able to get this super fast performance for that subset of the workload. But the majority of the workload is not, and is suffering from these high 15 millisecond sort of range latencies. Understanding the application I/O patterns is really the first step in in tweaking your system. And this particular, I just happen to have this slide from an SSD presentation, and knowing these patterns actually helps get the most out of your SSDs. But not just that, also spinning disks, caches, memory caches, storage arrays, and so on and so forth. So that's the thrust of the conversation today. There is one little thing that I wanted to say, which is that there are times where the simple shape analysis is not enough, and there's a whole bunch of different reasons why I won't go into it. We'll do that another time. But once in a while, you actually have to do trace analysis. Now, luckily, vSCSIStats also supports that, and this is an example of a trace of IOs from a desktop workload plotted over time. Time is on the x-axis, and the y-axis is the block range. So if this is a virtual disk, then all those little data points are IOs that were issued. See all kinds of patterns here, vertical strides, horizontal slices, as well as diagonal ones. Workload shapes are important, but some aspects of them, like the IO sequences, are actually sometimes critical. So the whole idea of combining these workload shapes with the data access pattern level information can be combined with simulation prediction algorithms to then go and actually get to the very high level accuracy, which I as a human am not able to do. I need a machine to go and do that. It's just too much data for me to process. And so that's this area where I think we're going to start to see a lot of innovation happen. The company that I work for happens to have investments here. But I think just in general, we're going to see a lot more of that sort of thing, of letting the machine do the analysis, because it's the amount of data that's needed for these sorts of things started to grow quite a bit. And just sitting there and doing hand calculus with this is just not going to scale. So to close, I would say that this tool is available. It's easy to use. It's real time. You don't have to wait for results. And if you need to store results away, that's easy as well. Would love to see more people try it out, and start a conversation in the community about how best to use these tools and how to help each other solve problems using these sorts of plots.
Excellent, Irfan. That was wonderful again. I think it's one of the key things here is kind of demystifying what vSCSIStats can do for you, because I think there has been a lot of perception, including my own perception, that the tool's not particularly approachable, and clearly it is a tool that we can use. Once we get over, for some people, the fear of using anything but a GUI tool, hopefully people are growing past that and are getting used to the idea that command lines are their friends, and that these tools can give them vast amounts of information very quickly without a GUI. Now we're coming back. Yeah,
I was going to say that I hinted at this earlier, that I'm actually kind of in fact I stayed up late tonight waiting for the session to start, and what I was actually doing was actually coding up a little project to go and automate all this data collection and visualization, so that we can get past even the command line hurdle and just really make it super easy for everybody to start to collect this data. So I'm actually looking for beta testers for that, people who would actually use it and try it out in their environments. So this is a shout out to everybody to say, look, if If a GUI version of this, which is completely automated and doesn't require you to go and log into ESX even to get access to this real-time data, if that's something that tickles your fancy, please write me a quick email and I'll add you to my beta list for that tool.
All right, and people can get hold of you as Irfan at cloudphysics.com or on Twitter as Virtual Irfan. We're coming back in 2 weeks' time to have a look at the fight over storage performance, as you've called it, as the culprits and victims, and we'll look some more at that solid state for usefulness forecasting that you gave a little hint on. The 19th of June is what we've got that one set down for. So still got a nice pipeline of Irfan. We're not going to release them anytime soon, and we'll keep dragging you out at 3 o'clock in the morning your time. I really appreciate you staying up for us.
Absolutely, my pleasure. Would love to continue to engage with people offline as well and carry the conversation forward. The more that I hear about how people would like to use these tools, not just this one, but other tools as well. I do a lot of hacking for stuff like this to help people out on the side. So just let's keep the conversation going.
All right. Again, thank you very much, Irfan. This has been the APAC edition of the vBrownbag podcast, and we'll see you again on the 5th of June. We'll be returning. Good night, everyone.